Now on to molecular geometry. So what we were just talking about was electron domain geometry. Molecular geometry, on the other hand, can be a little bit different. And you'll notice in the definition, the difference is the arrangement of bonded atoms. Notice it does not say domain, so this is not including lone pairs. Now, the reason being is that when you actually have a molecule, you don't see that lone pair there. Now, it's there and it repels, like in the electron domain geometries, but you can't actually see them with your eyes. If we were to actually blow up a molecule and its shape and such, you don't actually see those electrons there because they're not bonded to anything. So what we see is called the molecular geometry. Okay, so essentially when we're looking in there, it's lone pairs affect the shape because they do. For example, if it's one of these here, I've got 3 domains. Even if this is a lone pair, I'm still going to get 120-degree angles. So the angles are always based on the electron domain geometry. It's just that like you can't see one of them. So instead of this molecule actually looking like a trigonal planar, all we see are these 3 atoms, and that looks bent. That's what that's called. Okay, so when there are lone pairs on the central atom, the electron domain geometry and the molecular geometry are different. Okay, if there's no lone pairs, however, the electron domain geometry and the molecular geometry are the same. Okay, so if it's all bonds, so if this all of these guys, okay, these are all bonds. If it's all bonds, then whatever their electron domain geometry, it's linear. It is also linear for molecular geometry. It's only when you start adding in or having electron pairs on the central atom that you get differing molecular geometry. So like instead of this one being trigonal planar, which is its electron domain geometry because it's got 3 domains, it's actually called bent because what we see is bent. So there are some other shapes that you are going to have to know. So this molecule here, even though we draw our Lewis dot structure like this, Lewis dot structure doesn't take into account 3 dimensions. I have 1, 2, 3 domains. I have 3 things on it. So its electron domain geometry is still trigonal planar. But I can't see these, though the angle is still 120, so we call this bent. The shape of this is bent. And so I am going to have a chart with these molecular geometries on it as well. So if you have 1 domain that is lone pairs and 2 domains that are bonds, it's called bent because that's what it looks like. So why is the molecular geometry different when you have those electrons? Again, the electrons exist there. This is a great example. We will use ammonia a lot. You have nitrogen with 1, 2, 3 hydrogens and a lone pair. So they're still repelling. That lone pair and those hydrogens all repel each other because they're all electrons. And so we would be like, okay, this has 1, 2, 3, 4 domains. So this is going to be tetrahedral in electron domain geometry, but we can't actually see this lone pair. All we see is this shape down here. It's kind of standing up. So it's not trigonal planar because it's got 109.5-degree angles. It's also not tetrahedral because we can't see this lone pair up here. So there's another word for that molecular geometry. Okay, so if there are lone pairs, molecular geometry is different than electron domain geometry. So what are they? Okay, this next chart has all of the ones you will need to know in it. Okay, notice all of these are talking about ones with lone pairs. So if you have 3 total domains, one of which is a lone pair, that's how you read this chart. These 2 are for 4 total domains if one of them is a lone pair or if 2 of them are a lone pair. 5 if 1 is a lone pair, 2 is a lone pair, 3 is a lone pair, and 6, you only have to know if 1 is a lone pair or 2 is a lone pair. So if you have 3 domains, one of which is a lone pair, we already looked at one of these. Its electron domain geometry is still trigonal planar. It's still got 120-degree angles. However, one of them is dots, so we can't actually see it. So it's called bent. It looks bent. And I give you an example over here. Okay, if you have 4 and we swap out one of these on this tetrahedral molecule with dots, it looks like this. My angles are still 109.5, so it's not trigonal planar. This is also actually called a trigonal pyramid because it stands up because it's got 109.5-degree angles. These are not 120s. NH3, again, is one of those examples. So this is called a trigonal pyramidal or trigonal pyramidal molecule because it's 3, but it's standing up. Okay, so, and then if it's 4, we still have our 109.5-degree angles, but we swap out 2 of them with lone pairs, then it actually looks bent. So that is also bent. So you can have a bent with 120-degree angles, or you can have a bent with 109.5-degree angles. It just depends on how many total domains it has and those repulsions. Okay, 5 gets a little more complicated, right? This is our trigonal bipyramidal molecule. I'm going to start subbing some of them out with electrons. So when that happens, it's going to be the equatorial atoms that sub out with electrons. So if I have 4 domains and 1 lone pair, it looks like this. Okay, my angles are still 120 and 90, but this looks like a seesaw if you look at it sideways, like it's standing up, and that's the seesaw. So it's called seesaw shaped. I think active chemistry calls it sawhorse, that's what they call it. But it's the same thing. So if you have a molecule that has 5 total domains, but one of them is a lone pair, you get seesaw shaped or sawhorse. If you have 5 total domains, 2 of which are lone pairs, so we've subbed out 2 of those 120-degree angles with lone pairs. You can see this. These are going to be all 90-degree angles. It's called T-shaped. Looks like a T. Okay, you sub out all 3 of my middle ones with lone pairs. All I have are my axial atoms. I can't see the ones in the middle, remember, because they're electron pairs. It looks linear. So you can have a linear shape with either just 2 domains, no dots, or if I have 5 total domains, 3 of which are lone pairs, you also get a linear molecule. A little crazy. All right, and then for 6 total domains, you only have to know if we have 1 of them that is a lone pair or 2 of them. If 1 of them is a lone pair, you just sub out literally any of these because they're all 90 degrees apart. So I do it down here. This is called square pyramidal, because if you connected all of your lines on the outside, you would have a square on the bottom and it would be a pyramid. So it's called square pyramidal. You sub out 2 of them, then you get this flat square. So it's called square planar. All right. So the way you look at this chart is for when you have lone pairs. If you don't have lone pairs, you don't need to look at this chart. You go back to this one, and whatever their electron domain geometry is their molecular geometry. The same thing. Okay. If you have lone pairs, it actually changes. So make sure you look at this chart. I really like this one. Nope, hang on. Okay, I think I just wanted to show you this 3-dimensional thing. And they have, some of them have a little bit different names, but if you want just a quick representation of all of these, I just kind of like this link. So keep that in mind. Okay, I am going to go through all of the steps to determine the electron domain and molecular geometry. So if I'm asking about the shape, if I'm like, what is the electron domain geometry or what is the molecular geometry? You have to first draw the Lewis structure, because if you don't know if there are dots on the middle or not, which you can't know unless you draw the Lewis structure, you're going to get the shape wrong. So always draw it first. Even if it's a multiple choice question on the exam, always draw it first. Okay. Then you can determine the electron domain geometry. Remember, that's based on the total number of domains. That tells you your angles, and then the molecular geometry. So that might be different because if you have dots on the middle, then it's going to affect your shape. So you have a different molecular geometry than the electron domain geometry. Okay, so we're going to do a couple of these together. I'm actually going to pause this and erase this so we can do some together. Okay, so the first one is SO3. So I'm going to draw my Lewis dot structure. I'm going to put S in the middle, O, O, O on the outside. SO3, they each have 6 valence electrons, so 6 times 4 equals 24. So I need a total of 24. So I am, according to my Lewis dot structure rules, going to fill up the outside first. And then count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Awesome, I have 24. However, my last step is to check my octets. Well, my oxygens are good, but my sulfur in the middle is not. So I'm going to make one of these, into a double bond. So now my octet rule is good. So now it's a double bond. Okay, you could have put it anywhere. So now I have my structure. So you draw your Lewis dot structure, then you determine your total number of domains. So this has 3 domains, right? This is 1, 2, 3, and they all repel each other as much as possible. So I'd be like, okay, the electron domain geometry is trigonal planar. Okay, the molecular geometry, then I have no dots on the middle, so it is exactly the same. It is also trigonal planar. I don't know where my thing went. And you can't just say trigonal because there's also trigonal pyramidal, so you got to take that into account. All right, so if there's no dots on the middle, it is exactly the same. Okay. Okay, so then the next one is ICl4 minus. ICl4 minus. So I have I in the middle, CO, 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 fill in all my dots. Okay, these each have 7, so 7 times 5 is 35. This negative here means you add an electron. So I actually have 36 electrons. And currently I have 2, 4, 6, 8 times 4. Oops, 2, 4, 6, 8 times 4. That's 40. Hang on, I did something wonky. 7 times 5 is 35, 36, 2, 4, 6, 8, 10, 12, 14, 18, 20, 24, 26, 28, 30. Oh, 32. Sorry, I'm mathing incorrectly. So I currently have 32, so I have 4 more electrons. Well, when you have extras, where do you put that? On the middle. Okay, so this is the actual Lewis dot structure. And it is a negatively charged ion, so I'm going to go like that. Now I'd be like, okay, how many total domains does this have? 1, 2, 3, 4, 5, 6. So 6 total domains means my electron domain geometry is octahedral. Okay. Now I have 6 total, but 2 of them are actually dots, means that that's the 2 top and bottom that are going to go away from the octahedral. So this is 2 electron pairs and 4 bonded atoms, means that my molecular geometry, the thing I actually see, is square planar. Square planar. So in this case, my electron domain geometry and my molecular geometry are different because of those dots on the middle. Okay, so the other thing I want to introduce is the fact that not all electron domains repel exactly the same. They are very similar. So like if you have 3 domains, yeah, the angles are about 120, but if they're not all exactly the same, they might be a little bit slightly different than 120. So actually lone pairs repel a little bit more than bonds. For example, if you're looking at ammonia that has 1 lone pair and the 3 hydrogens, we would assume it has a 109.5 degree angle, which you can still repel exactly the bond angles. But in reality, it's actually about 107 degrees because the lone pair up here repels a little bit more than these bonds do. So we actually end up with about 107 degrees. So the lone pairs affect the shape just slightly more. So sometimes the angles are not perfect. And you can actually see that in our PhET simulation here. Let's go to real molecules. So this is a water molecule. Okay. It has 4 domains. So we would assume 109.5 degree angles, which if I asked you for the angle, saying 109.5 degrees is great. But the actual angles are 104.5 because these electron domains repel just a little bit more than a bonded domain does. Now, I would like you to try example number 2. So go ahead and pause it and then check your answers. Okay, so the answers here are CO2, Lewis dot structure looks like this. There's no lone pairs on the middle, so it is linear for both 180 degrees. SCl2 looks like this. It has 2 lone pairs and 2 bonds. So if I just said draw the Lewis structure, this is completely fine. Because like I said, Lewis dot structure does not take into account 3 dimensions. This would be a better representation of the Lewis dot structure, but either is fine because it is tetrahedral. So we assume 109.5 degree angles. However, we can't actually see those electrons. So it actually looks bent. So its molecular geometry is bent. You could also say that the angles are probably slightly smaller than 109.5 degrees. But if I ask for the angle, 109.5 degrees is fine because you know it has a tetrahedral electron domain geometry. And then CO3 2 minus looks like this. It has 1, 2, 3 domains. So its electron domain geometry is trigonal planar. No dots on the middle. So its molecular geometry is also trigonal planar. And it has 120 degree angles. Now, sometimes I might give you a larger molecule to look at. And in that case, when you have a more complex molecule and you're like, I don't know what central atom I'm looking at, you actually look at each central atom individually. So for more complex molecules with multiple central atoms, look at each central atom separately. So this is a central atom and has a specific shape, and this is a central atom and has a specific shape. So the carbon in this molecule has 4 total domains, is tetrahedral, tetrahedral. Whereas the oxygen here does have 4 total domains, but it is tetrahedral. bent, which actually affects the shape and properties of this molecule. This is methanol. Okay, so example number 3 says acetic acid, which is the substance that gives vinegar its characteristic smell and sour taste, is sometimes used in combination with corticosteroids to treat certain types of ear infections. Its Lewis structure is below. Determine the molecular geometry around each of the central atoms. I would just go ahead and find electron and molecular if I were you, and the approximate bond angles in the molecule, which if any of the bond angles would you expect to be smaller than the ideal values. So right when we've got dots. So there is a central carbon here, which is tetrahedral 109.5. A central carbon here, which only has 1, 2, 3 groups. So it would be trigonal planar with 120-degree angles. And an oxygen here that has 2 bonds and 2 dots, which means it is bent and has about 109.5 degrees, or probably slightly smaller than that 109.5 degree.